Welcome back to Wild and Crazy Physics 152 online. Having talked about electric charges, the electric fields that they produce, the forces that they exert on other charges, and how to calculate those fields and forces, now let's turn to electric dipoles, which are collections of charges that are bound together. And the simplest case would be just two equal and opposite charges like you might have in an ionic molecule, bound together and separated by a distance d. So polar molecules, hydrogen chloride for example, are a good example of stable and permanent electric dipoles. So we measure their strength, and we'll see where this comes into play when we calculate the fields that they produce. We measure their strength through the vector p, which we call the electric dipole moment. And p is defined as, for a symmetric dipole, as the magnitude of the charge that the two charges have times the distance vector d, where d is always defined, at least in physics. The convention is that we define this in the direction from the minus to the plus charge. And so that vector is a very important quantity because it tells us the orientation of the dipole. So we would like to know in the next few minutes two things. What's the electric field produced by this dipole in its surrounding area? And then how is the dipole itself affected by an external electric field? It can't be affected by its own electric field, but if we put a dipole down in a region where there is an electric field, we will see that it experiences an effect, and we will quantify that. So, how to calculate the field of an electric dipole? The exact field is simply given by the superposition of the fields of the two individual point charges. And so we could easily calculate what that sum is at a particular point in the vicinity of the dipole, but we can make a useful approximation, especially valid when the distances that we are away from the dipole are large compared to the size of the dipole itself. So in a typical molecule like hydrogen chloride, this distance is on the order of 2 times 10 to the minus 10 meters. So if we're several times that distance away, then this is going to be a good approximation formula. So we set the calculation up by writing down what the electric fields are produced at point P by these 2 point charges. They're separated by distance d as shown, and we're going to measure the position as x compared to the origin. So the distance that will appear in these equations is the distance from the center of the dipole to the point in question. And so we know that the positive charge will exert a force given by the first given by the first term in the positive x direction. The negative charge will produce a field that is in the negative x direction, and it's going to be slightly smaller, right, because the distance x plus d over 2 is a little bit larger. So those two terms should be clear. When we do a little bit of work to factor out an x squared from both the denominator terms, we can pull that x squared out in front, leaving behind 1 minus d over 2x quantity squared and 1 plus d over 2x quantity squared. And now we're going to use one of the familiar approximation formulas that we've seen earlier in the course. So we'll write these two terms, instead of 1 over that quantity, let's write 1 minus d over 2x to the minus 2 power, and similarly with the second term. And now you should see where we're going with this. If the quantity d, which is the size, the physical size of the dipole, is small compared to x, which is in the denominator, then this term here, the fraction, will be much smaller than 1. And the binomial expansion theorem will allow us to get a good approximation for that quantity by just keeping the first couple of terms. And so you can remind yourself that 1 plus z to the nth power is given by this infinite series, and if z is very small compared to 1, then it's going to be a pretty decent approximation to just keep the first two terms. So what will that do with our terms for the electric field expression? Well, the first term will just give us 1 minus negative 2 times d over 2x, which becomes 1 plus d over x. The second term similarly gives us 1 minus d over x. There's a minus sign in between, and so this simplifies to give 2kqd over x cubed in the i-hat direction. We shouldn't be surprised that the overall result is in the i-hat direction because the positive term had a larger magnitude than the negative term. And so here you can see this product qd appears in the numerator of this expression, and this is why we give it its own special name. And so P, defined as the charge times the distance, appears in this expression. And you'll notice that in this expression the electric field decreases with the distance like 1 over the distance cubed, which is more rapidly than it does for a single point charge, where that quantity is 1 over the distance squared. And the dipole moment is a measure of the strength of this electric field. If a dipole moment is larger, the field it produces will also be larger. So this is the approximate expression for that electric field. Now, what effect does an external field have on a dipole? And so it's pretty clear just by looking at a sketch that this external electric field will cause the dipole to line up in a certain way relative to that field. So here's your dipole, and we're just drawing it as if it's at some arbitrary angle with respect to the applied field E. Now, if we analyze this carefully, you can see that the positive end of the dipole feels a force from the electric field that points along the direction of the electric field to the right. The negative charge feels a force to the left. And so if this dipole is free to rotate, assuming it's just, in empty space, then that will produce a net force of 0, but there will be a net torque about the center of the dipole. And so without taking the trouble, there's the sketch that shows those the directions of the forces, which individually add up to 0, but they produce a non-zero torque. And so without going through a careful derivation, it's fairly easy to write down expressions for those two forces and then calculate the torque about the center of the dipole. And there's a nice compact way to write down that torque in terms of the dipole moment and the applied field E as the cross product. And here in my diagram, it's a good idea to check to see if you remember how to do cross products. P cross E is in the direction into the page. So if you point your thumb into the page, your fingers curl around your thumb in the direction of the rotation sense. So the dipole released in this picture would rotate in the clockwise direction so that the P vector would more properly align with the applied electric field. So that's the preferred orientation. And we can also talk about what's the potential energy of this dipole in the presence of the electric field. You can see that if the dipole lines up with the field, that's the preferred orientation, so that should have a lower energy. If the dipole were to be opposite to the applied field, that should be a higher energy. And there's a consistent way that we can do a calculation that shows how much work it takes to rotate the dipole through a particular angle. And when you do that calculation, a nice way to summarize the result is that there's a potential energy associated with that dipole in the electric field that's minus P dot E. So our friend, the dot product, reappears here in a useful way. The minus sign is important because when P is parallel to E, the dot product is positive. But we know that that is the preferred orientation, so the potential energy there should be a minimum. Right? So that sign guarantees that when P is parallel to E, we get a negative U, which means a low potential energy. If P is opposite to E, the dot product is negative, which means the potential energy is positive. So there's a high potential energy if they're oriented anti-parallel. And so if the P is perpendicular to E, the dot product gives 0, and that would be halfway in between those two extremes. All right, so now that we know what the electric field is that's produced by a dipole, and we know the potential energy for the interaction of a dipole with a field, we can do this example. It's kind of an interesting one because in real systems, in nature, especially in biological systems, there are lots of important interactions between systems, between molecules that have dipole moments. And in particular, the way that proteins interact with various structures in living systems is governed by just this kind of interaction. Also, the water molecules that make up a lot of living cells are made up of dipole molecules as well. And so the interactions that important biological molecules like proteins have with one another and have with the water that makes up much of living cells is important. And it governs the way that those structures move and the way that proteins fold into conformations that are important in allowing them to function the way that they do. So understanding these forces is important. So we'd like to know for P1 and P2 oriented parallel like this along a fixed axis with their centers separated by a distance r, what is the potential energy of interaction, and then from that result, what's the force between those dipoles? So the field of P1 at the location of P2, a distance r away, can be written using the result that we already derived. So the electric field of dipole 1 at this position, a distance r away, is 2k P1, and I've written over x cubed because that was the result that we obtained in the previous slides. But now we're going to make a simple substitution and write that as 2k P1 over r cubed. And notice what I've done here, instead of writing the magnitude of P1 times the unit vector in the positive x direction, I've just called this P1 vector, so that P1 of course points in the positive x direction. And so those are equivalent expressions. So that's the field produced by dipole 1 over at the location of dipole 2. Now what's the potential energy of P2 in the presence of this field E1? And we know the expression for that too. U, the potential energy, is minus P2 dot E1. So that dot product is easy. P2 is along the x direction. E1 is also along the x direction, so the dot product would just be the magnitude of P2 times the magnitude of E1 times the cosine of 0, which is 1. So it's an easy calculation to do. We substitute in here 2k P1 over r cubed dotted into, 2k P2 over r cubed dotted into P1 because P2 is the quantity that's dotting into E1, and so we end up with minus 2k P2 P1 over r cubed. And again, that happens because P2 and P1 are parallel to each other, and that dot product just gives P2 times P1. So that's the potential energy, and notice that it's proportional to 1 over the distance cubed. Now how do we get the force from this? The force that P1 experiences, the force that P2 actually what this should say is the force on P2 acting, the force on P2 from P1. I have that backwards here. But in either case, it doesn't really matter which way we think of it, because Newton's third law reminds us that the force of 1 on 2 is the same as the force of 2 on 1, just in the opposite direction. So the relationship quantitatively, if I have a potential energy function, the force along a given direction is minus the derivative of the potential energy with respect to that direction. And so here, r is the x direction, but since we have our expression in terms of r, we'll write the derivative that way. And when we take this derivative, it's easy to see the 3 is going to come down in front, multiply the 2, actually it's a minus 3, and so minus 3 times minus 2 is 6, but there's a minus sign in the definition itself, so we get this expression. And notice how this compares to Coulomb's law. The force depends on distance. It falls off much more rapidly than the force between 2 point charges. That shouldn't be a big surprise. We know that the electric field produced by an individual dipole falls off like 1 over the distance cubed, compared to 1 over the distance squared if we had just a point charge. So these forces are much smaller, and they're much more limited in range, in distance, than when you have point charges. But these are precisely the kinds of dipole-dipole forces that are very, very important to the functioning of biological systems. And I wanted to go back before closing just one to the previous slide to make a mention of an important application of dipoles interacting with electric fields, and of course that's in microwave ovens. What does a microwave oven do? It imposes an electric field that oscillates back and forth. So it doesn't just point along one direction, but 60 times per second, if you plug your microwave oven into a wall socket, 60 times per second the electric field flips back and forth from one direction to the other. And so the dipoles then are experiencing torques first in one direction and then the other direction and back and forth. And since the rotation of those dipoles, which are largely water molecules in the kinds of things that we like to heat up in microwave ovens, since those rotations are somewhat hindered by internal resistive forces, well, that oscillating electric field causes a loss of energy into the medium where the dipoles exist, and usually that's in water. And so as those dipoles flop back and forth, they're losing some of the energy that they have to the water molecules themselves. That manifests itself in the form of heat, and so the temperature of the system rises. So understanding the physics of dipoles in the presence of electric fields has important practical applications. Hope this has been a good introduction to dipoles, and I will see you in class.